Right. Hi, everyone. So this lecture is chapter 5 as well. It's on the topic of resonance structures. So this is after, if you learn the Lewis structures. Um, this is sort of a more advanced lesson on the Lewis structures. So let's go to the board and show you guys what resonance structures are. This happens when there's multiple way in which you can put the double bond somewhere on your structure, or triple bond even, right? There are options of where you can put double or triple bonds and the structure looks identical. Then what you have is a resonance structure. So a good example of that is the nitrate polyatomic. Nitrate is NO3 negative. So collectively, these four atoms have a negative charge. We're going to go through the same steps for Lewis structures as we would any other, as any other Lewis structure, even if you have a negative sign. Okay, so I'll show you guys how to deal with that. So for N, we have 5 valence electrons, right? For oxygen, we have 6 valence electrons, right? But there are 3 of them, so you're going to do 3 times 6. And now, because there is a negative charge, remember what negative charge means. It means you have an extra electron, right? So if it's 1 minus, it means you have an extra electron. And so therefore, you should add 1, right? That's due to the negative charge. Now, if it was 2 negative, then you would add 2, right? If it was 3 negative, you'd add 3, okay? Now, conversely, if it was positive, then you would take away 1, right? So you say minus 1. Or if it's 2 plus, then you take away 2, right? So pay attention to that charge and then add or take away the electrons accordingly. So here in NO3 minus, we have a total of 24 valence electrons, right? Okay, and then same steps as before. You're going to want the central atom first. That's going to be your nitrogen, right? Between N and O, right? N is furthest from the noble gas. And then you spread the 3 oxygens around evenly. Okay, so we're just going to do it like that, right? Spread it around evenly. Then the next thing you do is put in your bond, single bonds first. Okay, single bonds only. And then counting electrons, you'd use 2, 4, 6. So 6 from 24, you have 18 electrons left, right? Because we had 24 total. Okay. So now remember how we put the 18 electrons outside in, right? From the outer atoms to the inner ones. So notice it's 3 oxygens. They're all identical. So it doesn't matter, really where you start. You're just going to do it so that you have the octet fulfilled. So I put 3 pairs, right? So 2, 4, 6, 8. I have fulfilled my octet. Same here. Right? 2, 4, 6, 8. So this oxygen has octet and 2, 4, 6, 8 again, right? 2, 4, 6, 8. So once I've done that, you see I've already put in 18 dots, right? 18 dots. So I'm done putting in the dots. Then I check to make sure that everybody is happy with the octet. The oxygen's obviously happy because we made them happy, right? But is the nitrogen happy? Well, let's see. We got 2, 4, 6 only. So the nitrogen is not happy. It needs an octet. So what do? Remember, we put we move electrons for a double bond in order to get octet, right? So at this point, I can say, okay, I'm going to take that pair of electrons and I put it down to make a double bond. And I'm going to show the result, right, with an arrow. So I have now a double bond here. Okay. And then single bonded here. Okay. So I have now this nitrogen 2, 4, 6, 8. It has octet. This oxygen still has octet, right? 2, 4, 6, 8. And these 2 I didn't touch, so I know they have octet as well. So now the octet is fulfilled. I know I have my best structure. That's the best structure, best Lewis structure I can have. There's just one more thing that I'm gonna do, and you should do this anytime that you see an overall charge on a molecule. You want to put a bracket. Okay, and then say negative. Okay, so we put whatever charge that is. So this bracket, it's not a 7. Okay, it's a bracket. It's short for this, basically. But we're too lazy to draw a square bracket. So we just draw the corner of the bracket and we put negative, okay? So if it was 2 negative, then we put 2 negative, okay? But that's to denote that this whole entire structure is negatively charged. Okay, so don't forget to put that in there. Okay, now, at this point, you could have been like, hey, professor, why did you choose to take those 2 electrons and put it down for a double bond? Why did you not take these 2 electrons and do that? Or these 2 electrons and do that? And there lies the resonance structure, right? So we could have had a double bond here and here as well as here. So there are 3 separate places that we could make the double bond because there are 3 different oxygens, right? Even those oxygens are identical, okay? And so what's going to happen is that the resonance structure is going to look identical to each other. It's just that the double bonds are like in a different spot, right? So if I had taken these 2 electrons, then I would have had a separate resonance structure, okay, where the double bond is there, right? And then this oxygen still would have 3 lone pairs on it, right? And I still do brackets negative, okay? And notice what I'm, the arrow that I'm using to relate these two. This is called a resonance arrow. It's just basically a double-headed arrow, but it is a resonance arrow to denote that these two are in resonance with each other. They are resonance structures. So I can do a third one, right? There's a third one where the double bond's here. Right? And then single bonds here with 3 lone pairs, right? So these would be in resonance with each other, right? So you kind of have these 3, right? So 3 total, and again, brackets negative here. So I got 3 total resonance structures for NO3 minus. And what does that mean? It means that because electrons are always constantly in motion, and you guys know this, right? They don't ever stand still. The electrons of the NO3 minus molecule is actually spread evenly across the 3 oxygens, right? But if you just denote this one picture, let's say you just draw this picture, you would, misinform people that, hey, the electrons are only between this nitrogen and this oxygen. And that's not the true picture because electrons are constantly in motion and they're delocalized. That's the word that we use, which means they are spread evenly across the 3 oxygens. So you don't want to just put this picture. You also want to add these 2. So together, these 3 pictures give you the true picture of the nitrate anion, right? So 33.33% of the time, you would say this picture is the truth, as in the 2 electrons lie between these 2 atoms, okay? But another 33.33% of the time, the 2 electrons lie between this nitrogen and oxygen. And then another 33.33% of the time, it looks like that, right? So because the electrons are constantly in motion, that's why you need 3 snapshots, basically. There are 3 different snapshots of the truth, and together they form the picture of nitrate, right? And so that's what resonance structures are. Resonance structures are bits of the truth for that molecule. Not every molecule has resonance structures, right? And all the other examples in the previous videos that I've shown you guys didn't have resonance structures, right? But there are going to be some that will have resonance structures, and you want to be able to recognize when to draw all the resonance structures, right? So you want to be able to see that, I could have used electrons from the other oxygens to make the double bond, right? And so in short, that's how I think of it, right? It's like, can I put the double bond somewhere else, right? On an atom that is identical to the one that I put the double bond on, then that tells me, okay, I have more resonance structures. And when you come across a structure like that, you want to list all of the resonance structures that are unique, right? You can see that there are 3 unique ones, right? One to this oxygen on top, the double bond to the oxygen to the right, and then the double bond at the oxygen to the left. That's pretty easy to see. You can't make any more, right? And so you have 3. Okay, so be on the lookout for that. When you have a structure where you could possibly move, the double bond around and it's, it looks the same. Like these three, they kind of look, they pretty much look the same, right? It's just that the double bond's in a different location. Okay. Yeah, so let's do another one. So you guys get more practice. All right, so next, let's do HCO2 negative. So again, we have this negative charge, right? So hydrogen is 1 valence electron, carbon is 4, and then oxygen is 6, but you got 2 of them, so we're gonna do 2 times 6. And remember what we're gonna do with that negative sign? We'll do a +1, right? Because that negative sign means you have 1 extra electron. So total here would be 18, right? If I have that right, 12, 13 plus 5, okay, 18 valence electrons, okay? And then between these 3 atoms, right, carbon's going to be the central. Okay. Then we're going to put 1 hydrogen and 2 oxygens evenly around. So it doesn't really matter where you're going to have that, right? I'm just going to do it like this, right? And then we do single bonds. That's 2, 4, 6 electrons used. 6 from 18 is 12. We got 12 electrons left. How are we going to do that, guys, right? Outside in. The hydrogens don't need them. The oxygens do. So you're going to do 3 pairs on each oxygen. So that's 12, right? And then you're going to check carbon. Does it have octet? 2, 4, 6? No, it does not. These are 2, 4, 6, 8, 2, 4, 6, 8. Okay, so 2, 4, 6. No octet. So what are we going to do? We're going to have to put 2 electrons down for the double bond. And it doesn't matter which one I take it from, right? We're just going to do one first and draw the result. And we know that, okay, that's one structure already where I have a double bond on the top oxygen, single bonded to the bottom oxygen, okay? And now carbon has 2, 4, 6, 8, right? So it's got octet. We can do, again, brackets negative, right? To show that this whole molecule is negatively charged. And then, as you guys can see already, we have one more resonance structure, right? Just one, because there's another identical oxygen to that one, right? These 2 oxygens are identical. And I could have put a double bond there, right? So I'm going to show that, right? This is where I have the double bond. On the bottom oxygen, with 2 lone pairs, and then the top oxygen stays the same. So it's 3 lone pairs on that oxygen. So everybody has octet, right? 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. And we get, again, throw a brackets negative in there. Okay. So what do we have here? 2 resonance structures. 2 resonance structures, right? So what does that mean? 50% of the time, your double bond is here, right? 50% of the time, your double bond's here, right? And what that means is that the electron is spending its time equally between the 2 oxygen. And electrons do that, right? Because they're constantly in motion. So they're just basically just spreading their time evenly over these 2 atoms, right? And so that's why we got 50-50. Okay. Yeah. All right, let's do one more example. Let's do the carbonate anion. Carbonate is CO3 2 minus. So again, with our valence electrons, carbon has 4. Oxygen has 6, but there's 3 of them, so 3 times 6. And then the 2 negative tells you there are 2 extra electrons. You'd go add 2, right? That's because of the 2 negative. Okay, so total we have what, 24, right? 18 plus 2, 20, 24. Okay, So between carbon and oxygen, your carbon will be the central atom, right? Furthest from the noble gas. Then you're going to put your oxygens evenly around. You're gonna do single bonds, and you're gonna count 2, 4, 6 as your electrons used. You have 24 total. So 24 minus 6, you have 18 left. All right. And you want to distribute the 18 outside in. So you'll do 3 pairs on each of the outer atoms. Okay, that's 18. And then you're gonna do double bonds, right? Because the carbon needs octet and it doesn't have it right now. It just has 2, 4, 6. So you can swing this down and you can make it like that. Okay, and so now what you see is that this oxygen still has octet, right? 2, 4, 6, 8. This oxygen still has octet. We didn't touch it, right? 2, 4, 6, 8. This one too, 2, 4, 6, 8. And the carbon, which only had 6 earlier, is now 2, 4, 6, 8. Okay, so we're good. And we're gonna put, remember again, brackets 2 negative. Okay. And now it's kind of obvious to see, guys, like where else could we have made the double bonds? So how many more resonance structures do we see? 2 more, right? Double bond could be here or it could be here. And so you just draw it. Just go ahead and draw it out. Okay? Anytime you see that there is a possibility of other resonance structures, that's your task. It's just to draw it out, and that's it. Just exhaust all the unique resonance structures, and you're done. That's all you need to do. So for this last one, got a double bond on the oxygen to the left, and then the other two are single bonded. And then don't forget to use your resonance arrow to show, right? This is in resonance with this is in resonance with that, and this is in resonance with that. Right. And since, there are 3 of them, each of these represent 33.33% of the truth. Okay. And so that's why you need all 3, right? To basically denote the whole truth. Okay. Because only one of these is considered, if you just have one of these, it's only 33.33% of the truth, right? And so that's what you're going to do. Okay. So from now on, you have a structure, follow the steps, Lewis structure steps, but be on the lookout to see if, the double bonds can go in different places. And that's when you have resonance structures. And when you see that, make sure that you draw out all the unique ones that are possible. Okay. All right. So that's it on resonance structures.